Tonight, we imagine something surreal, something impossible, and yet entirely bound by the laws of physics. What would happen if the Earth just stopped spinning? Would we fly off into space? Would the oceans rise? Or would we just stop and sleep beneath the stars? Let's dive in. Chapter 1. The Earth's spin, why we don't notice it. The Earth spins, but we don't feel it. This fact is so deeply woven into our experience of being alive that we rarely, if ever, give it any thought. And yet this invisible motion shapes everything. The length of our days, the direction of the wind, the distribution of oceans, and even the rhythm of our sleep. The planet beneath your feet is rotating eastward at over 1,670 kilometers per hour at the equator, faster than the cruising speed of a commercial airliner. And still, the world feels still, quiet, unmoving. That calm is deceptive. We live inside a grand rotation. To truly understand what would happen if the Earth stopped spinning, we must first understand why we so effortlessly ignore that it's spinning in the first place. Earth's rotation is not a casual feature. It's the inheritance of billions of years of cosmic momentum. Our planet formed from the accretion of dust and gas orbiting a young star, all of it already moving. Angular momentum, the rotational equivalent of linear momentum, was conserved as these materials clumped together, creating a spinning sphere. That spin has never stopped. It has slowed slightly over time, largely due to the gravitational interaction with the moon, but it continues relentlessly, smooth and silent. Everything around us is moving with the Earth. The continents, oceans, atmosphere, and every living thing, us included, are part of this unified motion. We're not just passengers. We are embedded in the spinning frame. Because everything is moving in unison, we don't feel any jolt or resistance. There's no sudden acceleration or deceleration to trigger our senses. It's as though we're standing inside a sealed, glass-smooth train moving at constant speed. Toss a ball, and it lands in your hand just as if you were standing still. You're moving, but there's no way to know it from the inside. This is why you can look out at a serene lake, at trees barely rustling in the breeze, and feel convinced the Earth is stationary. But that is only a matter of perspective. The calmness is real, but the stillness is an illusion. Despite this, the Earth's spin does leave traces, subtle but profound, in the natural world. One of the most important is the Coriolis effect, a phenomenon that causes the path of moving objects, such as air masses, to be deflected to the right in the northern hemisphere and to the left in the southern hemisphere. The effect isn't caused by any real force. Rather, it emerges from the fact that Earth is rotating beneath the object's path. It's most noticeable in large-scale systems like hurricanes and ocean currents, which curve and spiral as a result. Without rotation, these systems would behave very differently, less organized, less directional, more chaotic. Another quiet signature of the Earth's rotation is Foucault's pendulum. This simple but profound experiment allows us to observe the planet's spin with our own eyes. Suspend a long pendulum from a high ceiling, set it swinging in one direction, and over time, it will appear to rotate. But it isn't the pendulum that's turning. It's the Earth that moves beneath it. Depending on your latitude, the rate of this apparent rotation changes. At the poles, the pendulum completes a full circle in 24 hours. At the equator, it doesn't rotate at all. It's a poetic reminder that even something so silent as rotation can be made visible with the right lens. We can also observe Earth's rotation in the cycle of day and night, though this is so embedded in our lives that we take it for granted. The rising and setting of the sun are direct results of the Earth turning on its axis. From the surface, it seems as though the sun moves across the sky. But in truth, we are rotating eastward into the light and then away from it again. The illusion is compelling but false. The sky does not move. We do. This rotation even affects the very force we call gravity. At the equator, centrifugal force caused by the Earth's spin reduces the effective gravity slightly, making you weigh a tiny bit less than you would at the poles. The difference is around 0.5%, not enough to feel, but enough to measure. This same force is responsible for the Earth's equatorial bulge. Our planet isn't a perfect sphere. It's slightly flattened at the poles and wider at the equator by about 21 kilometers. This affects satellite orbits, sea level, and even how water flows across the globe. Earth's spin also plays a vital role in maintaining the orientation of its axis. Like a spinning top, a rotating planet resists changes in the direction of its axis due to the gyroscopic effect. This helps Earth maintain a fairly steady axial tilt of 23.5 degrees. That tilt is what gives us our seasons. Without rotation, or with a much slower one, the planet would be more vulnerable to gravitational tugs from the moon or other celestial bodies, and the axis could wobble wildly or even flip. The result would be drastic, unpredictable changes in climate, shifting the zones where crops grow or where entire ecosystems can survive. Time itself is bound to this rotation. A day, 24 hours, is defined by the Earth turning once relative to the Sun. But Earth's rotation is not perfectly constant. Tidal friction caused by the moon is gradually slowing it down. Every century, the day becomes about 1.7 milliseconds longer. This may sound trivial, but over millions of years, it adds up. Hundreds of millions of years ago, a day on Earth was closer to 21 hours. In the distant future, a single day may last much longer than it does now. Because of this slowing, our methods of keeping time require occasional correction. Atomic clocks, so precise they lose less than a second over millions of years, occasionally drift out of sync with the gradually lengthening solar day. To compensate, we sometimes add a leap second to coordinated universal time. These are rare, but they are reminders that even the most accurate man-made instruments must bow to the subtle, continuous change in Earth's rotation. Biology, too, is shaped by this turning world. Nearly all life on Earth operates on a circadian rhythm, an internal clock tuned to the 24-hour day. Plants open and close in harmony with the sun. Humans sleep and wake on a cycle tied not just to culture or habit, but to a deep evolutionary adaptation to the Earth's steady rotation. If the day were suddenly longer or shorter, our bodies would struggle to adjust. Some species might adapt over generations. Others might fail to thrive. We are more connected to the spin of the Earth than we imagine. All of this, the weather, gravity, biology, time itself, depends on the fact that the Earth is turning. And yet we do not feel it. There is something almost poetic about that. We are rushing through space, spinning across the face of the cosmos, and the whole experience is delivered to us in stillness and calm. Perhaps that's why it's easy to forget. The world we walk on feels anchored, immovable, dependable. But that stillness is an illusion maintained only as long as the spin continues without disruption. If the Earth were to stop, even briefly, we would no longer be able to hide inside that illusion. The consequences would be instant and catastrophic. Everything we've ever known, our air, our oceans, our civilization, would suddenly be thrust into chaos. The calm surface we take for granted would become a memory. But for now, the Earth spins on. Every moment you're alive, the world carries you forward without effort. You don't have to think about it. You don't have to feel it. And yet, it is always there. In the silence between each breath, in the arc of the sun across the sky, in the tides and seasons and shadows, there is motion, constant, invisible, fundamental. And if it ever stops, everything changes. Chapter 2. If it stopped instantly the first few seconds. Imagine for a moment a world where everything continues as normal. The skies are quiet, the oceans breathe with the tide, and people go about their lives without realizing that a hidden momentum underpins every inch of their existence. Then, without warning, that momentum disappears. The Earth's rotation halts completely. Not gradually, not over millennia, but all at once. A full planetary stop. This is not just a thought experiment. It's a glimpse into physics pushed to its limit. A scenario where the familiar becomes fatal in the blink of an eye. In those first few seconds after Earth's rotation stops, everything we take for granted, motion, structure, atmosphere, would be flung into a state of unimaginable chaos. And we wouldn't even have time to scream. Because right now, where you're sitting, you're moving at about 1,000 miles per hour, or over 1,600 kilometers per hour, if you're near the equator. Every building, every tree, every molecule of air, every wave in the ocean is being carried at this same rotational speed. If that stopped suddenly, all of those things would try to keep moving forward. Newton's first law of motion, the law of inertia, would not kindly step aside. It would take over. Inertia is the universe's quiet refusal to change. An object in motion stays in motion unless acted upon by an external force. Earth's surface may stop beneath your feet, but your body and the air around you wants to keep moving. This would mean instant devastation. Entire cities, vehicles, and people would be launched eastward at immense velocity. Skyscrapers would collapse as their tops tried to outrun their bases. Highways would shred. Trees would be uprooted. It would be like the most violent winds imaginable. Except the winds wouldn't be blowing. They'd be lagging behind a world that just stopped under them. The atmosphere itself does not obey the planet. It's a fluid, and like all fluids, it retains its velocity until friction and pressure catch up. So while the Earth's crust halts, the air continues whipping eastward with terrifying speed. In equatorial regions, this would result in winds exceeding the speed of sound. Anything not solidly anchored, and even much that is, would be torn from the surface and hurled into ruin. Entire cities would be razed not by earthquake or fire, but by the air we depend on to breathe. And then there are the oceans. Water, too, carries forward with momentum. The oceans don't stop just because the Earth does. As a result, unimaginable tidal waves would race across the surface. Near the equator, massive walls of water would surge eastward, crashing over coastal regions, inundating continents. Even areas far inland might find themselves swallowed by the inertia of the sea. In the first minute, some of the world's largest population centers would vanish beneath hundreds of meters of water. It wouldn't just be a surface catastrophe. Deep inside the planet, shockwaves would begin to ripple. The sudden cessation of spin would create an immense imbalance in internal forces. The liquid outer core, no longer stabilized by centrifugal momentum, would churn irregularly. The crust would crack and buckle. Earthquakes would erupt along fault lines, many of them more powerful than anything we've recorded in human history. Volcanic activity would spike as pressure redistributed unevenly. What seemed stable would break. What seemed far away would suddenly be everywhere. In the skies above, the results would be just as jarring. Satellites in low Earth orbit are synchronized with the rotating planet. If the Earth stopped spinning beneath them, they would no longer be following a predictable path relative to the surface. Many would crash down, unable to maintain stable trajectories. The constellations of communication satellites, GPS, and surveillance systems would become a cascade of falling debris, creating further chaos. The artificial web we've woven around the Earth would unravel into streaks of falling metal. Even beyond the realm of infrastructure and terrain, there's another overlooked consequence: the human body itself. We're not built to handle that kind of abrupt motion. At equatorial velocities, your body would experience forces far beyond what is survivable. If you're inside a building, you would be smashed into the eastern wall at over 1,000 miles per hour. If you're outside, you would become airborne, dragged across the ground by winds and inertia that no plane or jet stream could compare to. The acceleration forces would be far beyond lethal. Muscles would tear, Bones would break before you had time to comprehend what was happening. Most living things would perish almost instantly. At higher latitudes, the effects would be slightly reduced, but only relatively. Near the poles, where rotational velocity is lower, some life might survive the initial moments. But they would not be spared from the environmental collapse to follow. The atmosphere and oceans don't respect borders. A planet-wide chain reaction would begin, radiating out from the equator toward every edge of the globe. All of this assumes an absolutely sudden stop, something that violates the laws of known physics. The energy required to bring the Earth's rotation to a halt instantly is beyond our capacity to imagine. It would require a force so vast, so immense, that it would likely destroy the planet in the process. But in this scenario, we're ignoring how it stops. We're only looking at what would happen if it did. Within minutes, weather systems would begin to break down. Without rotation, the Coriolis effect vanishes. Wind patterns that once curved gracefully now lose their structure, creating sprawling zones of chaotic airflow. Storms no longer spin, jet streams vanish. What remains is an atmosphere without order, a chaotic system in which weather becomes unpredictable, volatile, and extreme. With time, this breakdown would intensify, but even in the first seconds, we would see the seeds of it sprout. Perhaps one of the most surreal consequences would be what you'd see in the sky. If somehow you survived, you would watch the sun stop. Literally stop. It would freeze in place, hovering permanently in the sky. If you lived on the side of the Earth that was facing the sun at the moment of stoppage, you would find yourself under eternal daylight. No sunset, no nightfall, just an unblinking eye of fire, fixed above the horizon. The longer it remained, the more heat would accumulate, temperatures would rise, soil would dry, crops would wither, deserts would expand. On the night side, the opposite would happen. Darkness would become endless. Temperatures would plummet. Frost would creep across landscapes unprepared for eternal cold. The biosphere, adapted to cycles of day and night, would begin to fail. Plants would no longer photosynthesize, insects would die, food chains would collapse, and all of it would begin in those first, quiet, deadly moments when the spin stopped. These first seconds would be the loudest silence humanity has ever known. Not because they are truly silent, far from it. There would be wind and thunder and cracking earth and screaming metal, but the absence would be louder. The absence of movement we could control. The absence of predictability. The absence of a system we have relied on for every moment of human history. That absence would be louder than the roar of the storm. And then there is the deeper layer, the one that speaks not of wind and waves, but of memory and meaning. In the first seconds after Earth stops spinning, something else stops too, the continuity of experience. We've never lived on a motionless Earth. Everything from the shape of the continents to the rhythm of our breath has evolved under the influence of rotation. To remove that instantly is to break something not just in physics, but in identity. The Earth's rotation is a kind of heartbeat, and in this scenario, that heartbeat ceases. And yet this isn't just about disaster. It's about understanding how precious motion is, how reliant we are on a silent force that never asks for thanks. It reminds us how thin the line is between calm and chaos, how deeply physics defines not only what we see, but whether we continue to exist to see anything at all. In the first seconds, most of what we call civilization would vanish. But in that vanishing, we glimpse the truth. The Earth spins, and because it spins, we survive. Because it spins, the sun rises. Because it spins, we sleep and wake and grow. If it stopped, we would not. Chapter 3. The Death of Day and Night. We mark our lives by the rising and setting of the sun. From the soft light that spills across morning rooftops to the slow fade into twilight, the day-night cycle is not just a background. It is the rhythm by which life itself has learned to breathe. But if the Earth were to stop spinning, that rhythm would vanish. No more sunrise, no more nightfall, no ticking forward of the clock by the sun's shadow. The familiar dance between light and dark would collapse into a fixed division, a world of two extremes with nothing in between. One side of the planet would be locked in permanent daylight. The other would be cast into endless night. At first glance, it might sound poetic, a world frozen beneath an eternal sun, or asleep forever under a canopy of stars. But the reality would be far less beautiful, because this balance we take for granted, the balance of rotating into and out of sunlight, isn't just aesthetic. It's biological, environmental, and structural. It's necessary, and without it, everything begins to unravel. In a world where the Earth no longer spins, time itself becomes spatial. Instead of hours dividing the day, geography now does. Your place on the globe determines whether you live in burning light or freezing shadow. At the exact line where the sun's light permanently meets the edge of darkness, the so-called terminator zone, you might find a narrow band of tolerable climate. But elsewhere, survival becomes unlikely. Let's begin on the day side. Here, the sun would no longer move across the sky. Instead, it would hang fixed in place, unblinking. At the equator, it would sit directly overhead, pouring radiation down in a steady, unrelenting stream. With no rotation to distribute solar heat across the surface, the land beneath this eternal noon would begin to warm, then overheat, then burn. Unlike the current system, where the planet spins and heat is distributed more evenly, this locked-in exposure would cause temperatures to rise far beyond what any terrestrial life can tolerate. Soil would dry and crack. Plants would wither under the constant assault of photons. Rivers would shrink, evaporating into the thickening air. The oceans on this side would warm steadily, and surface temperatures could eventually reach the boiling point. Storm clouds, if they managed to form at all, would be sucked of moisture before they could offer relief. And it wouldn't just be the heat. Ultraviolet radiation, usually tempered by atmospheric mixing and planetary motion, would now concentrate over a single hemisphere. Skin exposed to this light would burn within minutes. Electronic systems might degrade faster. The atmosphere itself would respond to this unbalanced heating by expanding unevenly, creating massive upward convection currents that would distort local pressure systems and disrupt any remnants of predictable weather. On the opposite side of the globe, a different kind of destruction would unfold. Here, there would be no sunlight, no warming rays, just a deep, perpetual night that stretches on without morning. At first, it might resemble the peaceful stillness of a high-latitude winter, but the temperature would continue dropping, slowly but unstoppably. Without sunlight, surface heat would radiate away into space, chilling the landscape to subarctic, then Arctic, then sublunar extremes. Water would freeze, locking rivers and lakes beneath thick ice. Plants would cease all photosynthesis and then die. Animals, if they survived the initial halt, would struggle to find food. Entire ecosystems would collapse, not suddenly, but inevitably, as their energy source disappeared. It wouldn't be a violent end, like on the day side. It would be a slow suffocation, a world drifting into thermal entropy, 1 degree at a time. The sky, however, would be beautiful. In this eternal night, stars would shine without interruption. The constellations would no longer appear to move across the heavens. They would remain fixed, as though etched into glass. The moon, too, if visible, would become static. No phases, no rising or setting, just a suspended orb hanging forever in the same patch of sky. But even this beauty would be a cruel illusion. The night sky, for all its grandeur, would be watching over a world falling asleep in the deepest, coldest sense of the word. At the line between day and night, the twilight belt that forms a narrow transition zone along the terminator, there may exist a fragile opportunity for balance. Here, the sun would sit low on the horizon, neither rising nor setting, but casting long shadows across a motionless landscape. This thin region, stretching perhaps hundreds of kilometers across, could become the last refuge of life. Not because it's ideal, but because it's survivable. Temperatures here would be less extreme. Some warmth would bleed over from the daylight side. Some cool air would drift in from the night. This dynamic equilibrium could allow for pockets of habitable climate, an eternal dusk where water remains liquid and temperatures remain within biological limits. In theory, humans and other species might adapt to survive here, but in practice, the logistics would be daunting. Agriculture would be nearly impossible. On the dark side, photosynthesis would cease entirely. On the bright side, crops would overheat and die. Only in the twilight might specialized plants endure, but with no day-night cycle to regulate their growth, everything would have to be re-engineered. Human circadian rhythms would need to be artificially maintained. And over generations, even our biological clocks might begin to slip, confused by the absence of light-based time. Electricity, once the great equalizer of human civilization, would now be mandatory for survival. Artificial lighting, heating, and cooling would be required on an unprecedented scale. But the infrastructure needed to generate and distribute energy under such conditions would be difficult to maintain, especially when most of the world is now either underwater from atmospheric shock or frozen solid. And then there's the psychological toll. Humans are not designed for a static sky. Our ancestors followed the stars, measured time by the sun, lived their lives in sync with the light. A world where that light no longer moves would feel alien, even if it's technically Earth. Time itself would feel broken. We'd look at our watches and see the hands move, but the sun would not. The rhythm of sleep, work, social interaction, all would need redefinition, and it's not clear how well our minds could adapt. Over time, climate effects would deepen. The heated day side would continue absorbing solar energy, while the night side would continue shedding it into space. This thermal imbalance would create slow but immense currents in both the atmosphere and oceans, as hot air tries to flow into cold zones and water redistributes itself along temperature gradients. The Coriolis effect, gone now, would no longer guide these flows into spirals or organized jet streams. Instead, we'd see chaotic currents, swirling aimlessly, driven only by the relentless push of thermal contrast. Even tectonic processes might shift. The Earth's crust, responding to the uneven distribution of mass and temperature, could crack and move in unexpected ways. Ice would build on the night side, increasing pressure on the crust there. Oceans might pool in new configurations. Mountain ranges might grow, bend, or fracture under the shifting weight. The balance the Earth once maintained through spin would now falter, like a tightrope walker without a pole. It is hard to imagine the philosophical impact of such a change. The sun, once our clock and our compass, would become a reminder of what was lost. It would no longer rise or set. It would simply be silent, fixed, indifferent. The moon, too, would no longer cycle through phases or shift across the night sky. The stories written in the stars would no longer move. The great celestial clock would stop, and with it, our sense of orientation in both space and time. Perhaps in this world, calendars would become obsolete. Holidays tied to solstices or equinoxes would lose meaning. The ancient relationship between humanity and the heavens would be severed. A child born under eternal noon would never know the comfort of stars. A person growing up in permanent night would never feel the warmth of morning on their skin. Generations would grow, live, and die under one fixed sky. And yet, even in this frozen world, life might endure. In geothermal pockets, beneath the ice, in engineered twilight cities, in submarine ecosystems cut off from the surface, life could adapt. Not easily, not beautifully, but persistently. Because life has a way of doing that, even in the most unthinkable places. Still, the death of day and night would be more than a scientific event. It would be a loss of rhythm. A silence where once there was movement, a pause where once there was progress. And in that silence, we might begin to hear the deep hum of dependence, the realization that we never really saw the Earth spin. We only saw what it gave us: time, warmth, pattern, meaning. Without it, we would still live, but not as we are. Chapter 4. The Collapse of Weather Systems. Weather is one of the most familiar yet unpredictable aspects of life on Earth. It is the conversation starter, the harbinger of change, the delicate balance between chaos and calm. Rain cools the earth, winds sweep away stagnant air, clouds paint stories across the sky. But what we call weather is not a random series of events. It is a consequence of motion, specifically the rotation of our planet. Remove that spin, and the system collapses. In the first moments after Earth stops spinning, as oceans surge and continents crack, another, quieter shift begins: the unraveling of the planet's atmospheric engine. Though less immediate than tidal waves or crumbling buildings, this change is just as devastating. It signals the beginning of a new era, one where the skies no longer move with purpose, where air, once vibrant and structured, begins to drift into a slow entropic stillness. To understand the collapse of weather, we must understand how it functions. Earth's atmosphere is a fluid, a massive envelope of gases heated from below by the planet's surface and above by the sun. The sun's radiation strikes the equator more directly than the poles, creating temperature gradients. Hot air rises near the equator, moves toward the poles, cools, and sinks, generating circulation patterns. These large-scale movements of air, known as Hadley, Ferrel, and polar cells, define the structure of our climate zones. But rotation plays an equally critical role. The Earth's spin introduces a force known as the Coriolis effect. This isn't a true force in the Newtonian sense. It arises from the rotating frame of reference. As air moves across the planet's surface, the Earth turns beneath it. This deflects the path of the moving air, causing it to curve rather than travel in straight lines. In the northern hemisphere, this deflection is to the right. In the southern hemisphere, to the left. This curvature is what gives rise to the swirling structure of hurricanes, the spin of cyclones, and the rotation of trade winds. It organizes chaos. It shapes turbulence into patterns. It is the unseen hand that gives weather its form. Take that spin away, and the Coriolis effect vanishes. Suddenly, the air no longer curves. Wind loses its structure. Global circulation cells dissolve into vast, slow eddies with no rotational guide. Storms unravel. The jet streams, those high-altitude rivers of fast-moving air that steer storms and regulate temperature, collapse. The atmosphere, deprived of its gyroscopic skeleton, begins to sag into instability. At the equator, the absence of Coriolis force means rising hot air no longer spreads out and curves as it moves poleward. Instead, it rises vertically and stagnates, creating zones of prolonged low pressure that don't redistribute effectively. Moisture, once carried by winds across continents, now lingers in place or falls inefficiently. Rain patterns become erratic. Regions that were once lush grow dry. Areas that were deserts might briefly see floods, but only until the system loses enough energy to move water at all. On the now motionless Earth, the sun's energy still reaches one side of the planet continuously. The daylight hemisphere bakes under constant radiation, heating the land and ocean surfaces. This heating causes the air to rise rapidly, but now with no global rotation to organize or disperse it, massive, slow-brewing updrafts form. These vertical columns of hot, moist air expand upward and outward until they lose energy. Without rotation, they don't twist into hurricanes. They simply grow, stall, and collapse. The result isn't structured storms. It's enormous, chaotic thunderhead systems capable of localized destruction, but without the elegance or mobility of cyclones. On the dark hemisphere, where the sun no longer reaches, cooling is inevitable. The surface begins to radiate heat into space, growing colder by the hour. The air above contracts, becomes denser, and sinks. In the absence of rotation, this cold air no longer flows along established pathways. Instead, it creeps outward like an expanding dome of stillness, suffocating movement beneath its weight. Any remaining weather systems caught within these zones begin to collapse under their own inertia. The contrast between the hot side and the cold side becomes stark. So stark that it generates immense pressure differentials. In the early stages of this post-spin world, these differences drive winds on a continental scale. But without the Coriolis force, they don't spiral. They rush in straight lines, from high-pressure zones in the dark toward low-pressure zones in the light. These direct, high-speed winds rip across the terminator zone, the thin region where day meets night, with ferocity. The atmospheric equivalent of tidal waves, these pressure gradients become the last vestiges of an organized sky. But even these, with time, fade. As temperatures stabilize, perpetual heat on one side, perpetual cold on the other, pressure differences begin to settle. The winds slow, the turbulence calms, not because balance has been restored, but because the system has died. Weather requires change. It thrives on imbalance. Without rotation to create and maintain those imbalances, the atmosphere slowly drifts into stagnation. Clouds, once sculpted into towers and whorls, now form in strange, still layers. Rain becomes an infrequent, localized event tied more to geography than climate. Some mountain ranges on the day side may still coax water from rising air, but elsewhere the sky is quiet. On the night side, moisture condenses into frost, then ice, and finally becomes part of the landscape. Snow no longer falls from storm systems. It settles gently as vapor freezes out of a still, bitter sky. Over decades, the oceans begin to react. Ocean currents like the Gulf Stream or Kuroshio Current are driven by wind and Earth's rotation. Without those drivers, the great conveyor belts of warm and cold water falter. Circulation slows. Nutrient upwelling diminishes. Marine ecosystems, already strained by atmospheric instability, begin to fail. Coral reefs bleach not just from temperature but from isolation. Fisheries collapse. Life in the sea becomes increasingly sparse. Meanwhile, inland areas on the permanent day side face relentless desertification. With no rotation to distribute moisture, arid zones expand unchecked. Soil dries out. Forests retreat. Grasses turn to sand. Insects disappear. Birds lose their migratory cues. Even the hardiest species begin to die off. Ecosystems don't just vanish, they unravel thread by thread. And through it all, there is silence. Not the kind that comes from a lack of sound, but the eerie, oppressive silence of a world that no longer breathes in rhythm. The Earth, once a dynamic engine of storms and winds and clouds, has become a place of fixed extremes. The sky still exists, but it has no weather. It has only consequences. Humans, if they survive the initial cessation of rotation, would find themselves facing a slow extinction by climate. We are adaptable, but only within a narrow range. Our bodies rely on certain temperatures, our crops rely on seasonal rains, our infrastructure depends on predictable weather. Without rotation, there are no seasons, no cycles, no variability to plan around. Just a brutal consistency, either unending heat or unending cold. Cities that once thrived on temperate coasts become uninhabitable. Power grids collapse under the load of cooling the bright side and heating the dark. Water supplies vanish or freeze. Even breathing might become harder in some regions as air stagnates and pollutants accumulate. Without wind, nothing moves them away. There may be a few places, in the terminator zone, at high elevations, near geothermal vents, where weather maintains some fragment of variability. These places might serve as sanctuaries. Enclosed environments with artificial climate regulation may allow a small population to persist. But humanity's golden age of meteorology would be over. We would no longer forecast storms. We would track the slow decay of a dying sky. There is, hidden within this collapse, a strange kind of clarity. We often treat weather as an inconvenience, something to be tolerated, managed, or avoided. But weather is a sign of life. It is a byproduct of motion, imbalance, and renewal. Storms rage because energy is moving. Winds blow because the planet turns. Rain falls because the Earth is alive in ways we rarely consider. Without that motion, we are left with a sky that no longer speaks, the clouds no longer gather with purpose, the winds no longer carry the scent of distant rain. The sky becomes a painting, beautiful perhaps, but lifeless. And so, when we look up, we may come to miss even the storms. Chapter 5. The tectonic shift and earthquakes. When we imagine Earth without its spin, we often think of what happens on the surface: winds, oceans, climate, light. But beneath our feet, below the crust that holds our cities, forests, and memories, lies a dynamic world in motion. A world that breathes heat, pressure, and molten rock. It is a planet that is not solid in stillness, but alive in tension. And when the Earth stops spinning, that deep internal balance begins to shift. At first, the effects are indirect. The sudden loss of rotation doesn't instantly crack the crust or unleash volcanoes. But as hours turn to days and days into weeks, stresses begin to accumulate where once there was equilibrium. Earth's outer shell, its tectonic plates, float atop a semi-fluid mantle. This mantle flows over geological time, slowly churning with convection currents driven by heat from the core. That heat, in part, is regulated by the distribution of surface pressure and mass. And one of the most powerful stabilizers of that system is the planet's rotation. The spin of the Earth helps distribute mass symmetrically. Centrifugal force, while subtle, creates an equatorial bulge, about 21 kilometers wider at the equator than at the poles. That shape is not a coincidence. It is the Earth's response to its own momentum, stretched like a balloon under rotation. Stop that spin, and the bulge begins to recede. But Earth is not a perfectly elastic body. It cannot instantly reshape itself to a new equilibrium. Instead, the crust begins to shift, slowly at first, then with increasing violence. The massive redistribution of weight toward the poles, triggered by the collapse of the equatorial bulge and the gravitational pull toward a now slightly more spherical shape, sets tectonic plates into unfamiliar motion. Continents that once glided across the surface with slow but predictable drift now feel uneven forces. The plates, which move just a few centimeters per year under normal conditions, are suddenly influenced by enormous lateral stress. Subduction zones, regions where one plate dives beneath another, become overpressured or starved of force. Rift valleys, once gently pulling apart, are twisted in directions they were never meant to go. Fault lines begin to slip. The earthquakes. These are not ordinary earthquakes. These are not the rumbling events that shake chandeliers or crack sidewalks. These are continent-shaking ruptures. Megaquakes. Some may exceed magnitude 10 on the Richter scale, a level never recorded in human history. The energy released would be catastrophic. Entire regions could be liquefied. Mountain ranges might shift in hours what they would normally in millennia. Cities near active boundaries, Tokyo, Istanbul, Los Angeles, Tehran, would be among the first to crumble, and the damage would not be isolated. This is a systemic response. Once the plates begin to move, chain reactions are inevitable. Tension builds in one fault line, then transfers to another. Earthquakes trigger earthquakes. Seismic waves race through the crust like echoes in a bell, setting off aftershocks for days or weeks. Some of these quakes would be so powerful that they reshape coastlines or force rivers to find new paths. And beneath the crust, something even more dangerous stirs. Earth's mantle is heated by radioactive decay and residual energy from the planet's formation. This heat creates convection currents, slow rolling waves of semi-molten rock that circulate material and move tectonic plates. But these currents rely on rotation, just like the atmosphere and oceans. Without rotation, the balance is lost. The patterns that once moved predictably begin to change. This change disrupts the heat flow from the core to the surface. Some areas may begin to cool more rapidly. Others, especially under thinning or fractured crust, may experience hotspots, regions where mantle plumes push upward with increasing force. The result? A global uptick in volcanic activity. Volcanoes awaken, Some may erupt violently, with pyroclastic flows racing down slopes and blanketing valleys in ash. Others may pour lava slowly, reshaping landscapes in silence. But the most dangerous effect may not be local. The ash and gases, particularly sulfur dioxide, released into the atmosphere could cause a drop in global temperatures, a phenomenon known as volcanic winter. This cooling would affect the Twilight Zone, the narrow strip between eternal day and night, where most human survivors may be clustered. Crops would fail, sunlight would dim, respiratory issues would rise. Combined with the collapse of weather systems, food supply chains, and infrastructure, this would further strain the chances of long-term survival. Meanwhile, undersea volcanoes erupt along mid-ocean ridges, building mountains beneath the waves, or collapsing into massive calderas that displace water and generate tsunamis. These waves, amplified by the inertia of oceans still adjusting to the new gravitational layout, strike coasts already weakened by tectonic quakes. And the feedback continues. As tectonic stress fractures more of the crust, underground reservoirs of gas and fluid are released. Methane, trapped beneath permafrost and ocean sediments, escapes into the atmosphere. This potent greenhouse gas could tip the climate balance, intensifying heating on the day side and causing strange weather anomalies in the already fragile Twilight Zone. In some regions, subsurface aquifers might collapse, leading to sinkholes the size of city blocks. Even the Earth's magnetic field, a vital protective shield against cosmic radiation, is not immune to tectonic disruption. The field is generated by the motion of molten iron in the outer core, and though the sudden loss of spin doesn't halt this motion instantly, it does interfere with its dynamics. Changes in heat flow caused by the altered mantle convection may weaken or destabilize the field. Over decades or centuries, this could lead to magnetic anomalies, or even a full magnetic reversal. During such transitions, the protective field weakens dramatically, exposing life on the surface to higher levels of solar and cosmic radiation. There's something haunting about this cascade. It is not violent in the way a bomb is violent. It is slow and grinding. The Earth is not exploding. It is rearranging itself, quietly, irreversibly, as if the planet is trying to find a new shape for a new kind of stillness. And what would this new shape be? A more spherical Earth, free from its equatorial bulge. A new equilibrium formed by gravity alone. Oceans migrated toward the poles, continents warped and broken. Volcanoes remapping the surface from below. Mountains pushed up, not by collision but by collapse. A new geography, a post-spin Earth, no longer recognizable. For those who survive, the world would feel unfamiliar beneath their feet. Old fault lines might have vanished. New ones would have opened. Ancient tectonic patterns, hundreds of millions of years in the making, reset or destroyed. Future generations, if they come, would grow up with no understanding of the way things once were. No maps would match the land. No histories would explain the scars on the Earth. Perhaps most sobering is this. Tectonics is the slow pulse of a living planet, the movement of continents, the recycling of crust, the drift of ecosystems over epochs. It is the geologic rhythm of Earth's breath. And when the spin stops, that rhythm stutters. Not instantly, but over decades, then centuries, the dance slows, the balance breaks. And yet, beneath all of it, the mantle still moves. Even without the guidance of rotation, the Earth's deep interior is not entirely still. It groans and stretches and adjusts. The planet does not die, it changes. Perhaps that is the most difficult truth, that catastrophe is not the end. It is the beginning of something else. But for us, creatures of the surface, used to the solid ground beneath our feet and the illusion of permanence, this slow upheaval would feel like the undoing of everything. Streets would break, mountains would rise where plains once lay, volcanoes would swallow valleys that had stood untouched for ages, and the sky, calm and indifferent, would watch as the Earth beneath it tore itself apart, not in rage, but in reconfiguration. We often think of Earth as steady, as our anchor in the cosmos. But it is not solid, it is not fixed. It is a body in motion, from surface winds to molten core, from tectonic plates to spinning skies. When one motion stops, another begins. And in that transfer, in that imbalance, we find the cracks that remind us the Earth is not still. It never was. Chapter 6. The oceans march toward the poles. When the Earth stops spinning, the effects ripple outward, not just through the air or the crust, but through every drop of water on the planet. The oceans, vast and deep and ancient, are no exception. In fact, they may be the most visual and dramatic indicator of what happens to a world that has lost its motion. Right now, our oceans are shaped by the same quiet force that sculpts the Earth's bulge at the equator: centrifugal force. As the Earth rotates, this outward-flinging force pushes water slightly away from the axis of rotation, encouraging a subtle but crucial redistribution of mass. The oceans, like the atmosphere, are fluid. They obey gravity and momentum, and under constant spin, they are not level in the way we might imagine. Instead, they are slightly puffed outward around the equator. This bulge may not seem like much, only about 8 to 10 kilometers of additional sea surface height, but it holds vast volumes of water. Water that, upon the halting of Earth's rotation, will no longer have any reason to remain where it is. And so it will begin to move. With the planet at rest, the centrifugal force that helped balance the shape of the seas disappears. Gravity reasserts itself with uniform pressure, and the oceans begin a slow, relentless redistribution. No longer held outward by momentum, they start to migrate toward the poles, where the curvature of the Earth draws them inward, where gravitational potential becomes slightly lower, and where water seeks new balance in a world that has lost its rotational symmetry. This is not an event marked by roaring tidal waves or crashing surf. It's not the cinematic deluge of flood myths or disaster films. It is more terrifying in its silence. The water rises slowly but steadily. Coastlines change over months, then years, then decades. Regions near the equator, once rich with life and densely populated, begin to dry. Harbors empty. Coral reefs bleach and die in shallow pools of warming water. What were once vast oceans begin to recede, revealing muddy seafloors littered with shipwrecks and long-buried geological features. At the same time, the poles swell. Sea levels near the polar regions rise dramatically, flooding tundras, swallowing permafrost, and transforming icy landscapes into brackish, shallow seas. Northern Canada, Greenland, and Siberia begin to vanish beneath encroaching waters. Antarctica becomes a fractured archipelago of ice-capped islands. In the north, Russia's Arctic frontier floods. Cities built on the assumption of permafrost permanence find themselves underwater or washed away by the slow tide. This migration isn't simply a matter of coastline change. The consequences are planetary. Ecosystems collapse as salinity shifts, temperatures fluctuate, and species lose their environments. Entire biomes, estuaries, mangroves, salt marshes, disappear in the shifting terrain. Creatures evolved for coastal living find themselves stranded in deserts or swept into colder waters they cannot survive. And with the migration of oceans comes the redistribution of weight. Water is heavy. The world's oceans, when moved even slightly, exert tremendous pressure on the crust below. As water drains away from the equator, the land there begins to rise, very slowly, responding to the sudden release of pressure. This is a process known as isostatic rebound, and while it usually occurs after the melting of ice sheets, the same principle applies here. The Earth's crust flexes upward, cracking in places, altering landscapes, and further contributing to tectonic instability. At the poles, the reverse happens. The crust sinks under the new weight of accumulating oceans. This subsidence can trigger new fault lines, awaken dormant volcanoes, or create vast inland seas. What once were mountain ranges may become islands. What once was a valley may disappear beneath kilometers of water. In time, even the map of the continents begins to warp. Human infrastructure, so carefully engineered to meet the demands of a spinning planet, is utterly unsuited to this new configuration. Cities like Jakarta, Lagos, and São Paulo, built near the equator, face gradual desiccation. Croplands dry out, ports become stranded far from the receding sea. Aquifers collapse as saltwater intrudes and groundwater vanishes. Trade routes die, societies fracture. Meanwhile, settlements near the poles become submerged. Places once seen as uninhabitable for agriculture or year-round residents now face both opportunity and threat. Some may try to migrate toward the water, seeking new coastlines for fishing or commerce, but the cold remains. Polar waters, fed by glaciers and unlit by sun, remain inhospitable for large-scale development. This redistribution of water also affects Earth's climate in unexpected ways. Right now, the oceans play a critical role in regulating global temperature. They absorb solar radiation, transport heat from the equator toward the poles, and buffer against extreme shifts in climate. The thermohaline circulation, often referred to as the global ocean conveyor belt, drives the movement of warm and cold water across vast distances. It relies on differences in temperature and salinity, powered in part by the Coriolis effect and prevailing winds. Without rotation, this conveyor belt collapses. The great gyres, massive rotating systems of ocean currents, cease to spin. The Gulf Stream, which keeps Western Europe warm, dies. The Kuroshio Current, which warms Japan, halts. Warm water stagnates in the shallow pools of the subtropics. Cold water pools in the polar regions without recirculation. The oceans, once dynamic and interconnected, become stratified, layered in temperature and density, and largely still. Without circulation, oxygen levels drop in the deep sea. Hypoxic zones, regions where oxygen is too low to support life, expand. Fish populations crash. Coral reefs die not just from heat but from suffocation. The oceans grow quiet, empty, lifeless. Vast blue deserts stretch beneath the surface where once life teemed. And so the world becomes divided, not only by light and dark, hot and cold, but by wet and dry. A swollen ring of parched equator, cracked and blistering under a permanent sun, flanked by rising oceans that creep slowly toward the poles. It is a planetary redistribution of mass and possibility. The symbolism is hard to ignore. Water, the giver of life, is moving away from the heart of where civilization began. The great river basins that supported ancient agriculture, like the Nile, the Tigris, and the Amazon, now run dry or are rerouted entirely. Humanity, once a coastal species, finds itself adrift inland or clinging to higher ground near the poles. The migration is not one of choice, it is necessity, and the sea, as always, is indifferent to our presence. As the oceans shift, they also change in chemistry. Without circulation, carbon dioxide absorbed from the atmosphere begins to accumulate near the surface, creating acidic layers. This ocean acidification accelerates, eroding the shells of marine organisms, dissolving coral, and disrupting food chains. Rainfall, influenced by the changing shape of oceanic evaporation zones, becomes sporadic and localized. Some regions face permanent drought, others drown under unrelenting cloudbursts. The planet's hydrological cycle, its great engine of evaporation, condensation, and precipitation, becomes fractured. No longer a smooth global loop, it splinters into isolated systems. Inland deserts expand, some become salt flats. Others remain lifeless, too dry for any form of recovery. In contrast, certain polar regions experience continuous rainfall or snowfall, creating glacial floods or boggy wastelands. And through it all, the sea continues to move. It is not malicious, it is not rushed, it simply obeys physics. Gravity calls, rotation releases, and the oceans obey. In the far future, the Earth will find a new balance. The seas will settle, the crust will stop groaning, the ice will melt or refreeze in accordance with new alien rhythms, but it will not resemble the Earth we knew. The blue marble we once photographed from space will look different. The great continents will wear new coastlines. The clouds will form in unfamiliar shapes, The balance between land and sea will tilt, as it always does, toward change. And humanity, if it survives, will do so by following the water. We are a species that came from the sea, that drank from rivers, crossed oceans, built harbors. We thrive near water. We fear it. We worship it. And when the earth stops spinning, it will move without us or take us with it. The oceans will not rage. They will not scream. They will simply go where they must. And when they arrive, they will rewrite the world. Chapter 7. Human Civilization in Twilight. There was a time when cities followed the rhythm of the sun. Markets opened with the dawn, curtains closed with the dusk. Human life flowed in tandem with the turning earth. But now, in a world where the earth has ceased to spin, that rhythm is broken. Day and night no longer come and go. Instead, they are carved into the land like borders, immovable, permanent, merciless. On one side of the planet, the sun remains fixed in the sky, burning down on everything without reprieve. On the other, darkness reigns, unending and absolute. But between these extremes lies a thin belt, a twilight zone. A narrow region where the sun hangs low on the horizon, casting eternal sunset or pre-dawn hues. This sliver of the earth becomes the last frontier for humanity's survival. It is not a utopia. It is not even truly habitable. But compared to the inferno of the day side and the frostbitten silence of the night side, it offers something rare: possibility. In this twilight region, temperatures are less extreme. The land is neither scorched nor frozen. There is just enough light for vision, just enough warmth to keep water from turning to ice. But even here, survival is a question of adaptation, ingenuity, and luck. Cities in the Twilight Zone would not grow as they once did. They would be carved from necessity, positioned carefully along ridgelines, riverbeds, geothermal vents, or surviving coastlines. Their architecture would resemble neither the skyscrapers of Manhattan nor the sprawl of Los Angeles. Instead, they would be low-slung, insulated, built into the earth itself, designed not for beauty or comfort, but for endurance. Solar panels would line every surface that faced the fixed sun. Every photon captured would be vital. Energy would be precious, powering pumps, filters, heaters, and artificial lights. Because although the sun glows softly on the horizon, its angle is low, inefficient for most modern photovoltaic systems. Entire infrastructures would be redesigned to chase light that no longer moves. Food production would become a central concern. Traditional agriculture, dependent on shifting sunlight, would collapse. Instead, massive underground or enclosed vertical farms would dominate, powered by artificial lighting and hydroponic systems. These farms would use recycled water, nutrient solutions, and genetically modified crops bred for low light or no light conditions. Crops like potatoes, lettuce, algae, or mushrooms, plants that can grow quickly and in limited light, would form the base of the new diet. Protein might come from insects, cultivated fish, or lab-grown meat. Luxury in this new world is anything fresh. Water scarcity would dominate planning. On the day side, evaporation would have already robbed many sources dry. On the night side, everything is locked in ice. Only in the twilight does water remain liquid, circulating through pipes, collected from condensation and filtered endlessly. Massive desalination and purification systems would be essential, operating around the clock to keep even small populations alive. Governance would change too. Old nations tied to geography and ideology would crumble under the pressures of survival. Borders would fade. Resources would redraw power lines. The largest organized societies might resemble tightly controlled city-states or nomadic enclaves moving along the edge of the Terminator, always chasing optimal temperatures and light levels. Language, too, might evolve. New terms would be needed for time, now that day and night no longer hold universal meaning. Calendars would be outdated. Clocks would tick on, but what they measured would feel hollow. Children would grow up never seeing a sunrise. Adults would forget what it felt like to watch stars disappear into morning. The very idea of time might begin to fragment, measured instead by power cycles, crop yields, or the timing of artificial light rotations. Culturally, this would be an era of mourning and myth-making. People would look back on the world that spun with a mixture of disbelief and reverence. Entire generations would be born into stillness, inheriting stories of seasons, time zones, and the rising sun. Some might not believe them. Others might turn them into religion, worshiping a sun that once moved, building temples on mountaintops where its light strikes just right, or fearing the dark beyond the horizon where cold death waits. There would be those who venture beyond the Twilight Zone, explorers, engineers, exiles. On the bright side, efforts would be made to harness the constant solar energy. Massive automated solar farms might be constructed, long chains of photovoltaic fields stretching across the scorched deserts. These would be managed by AI systems or robotic maintenance teams, insulated against extreme heat. The energy they produce might be stored in ultra-dense batteries or transmitted via superconducting cables back to the Twilight cities. But maintaining these outposts would be perilous. Temperatures would rise far above human tolerance. Electronics would fail under thermal stress, and solar storms, unbuffered by the planet's now weakening magnetic field, would strike the sunward side with increasing violence. On the dark side, other challenges await. With the atmosphere still, pollutants linger. The cold thickens the air until it becomes painful to breathe. Entire cities might be buried under growing ice caps or crushed beneath layers of hoarfrost. Yet there may be potential in the deep night. Geothermal energy, mined from volcanic zones or tectonic hotspots, might power small, isolated settlements. These cold-side colonies would be isolated, somber, focused entirely on utility. The psychological toll of darkness would be immense, requiring rigorous mental health structures, artificial day-night cycles, and controlled social environments to prevent collapse. Trade between settlements in the Twilight Zone and these outlying areas would be dangerous but necessary. Resources unique to each region, heat, light, minerals, ice, would need to be moved, exchanged, and protected. Specialized transport systems might develop. Autonomous vehicles crawling slowly across desolate landscapes, rail systems insulated against temperature swings, or even underground hyperloops shielded from the harsh conditions above. Communication infrastructure would be decentralized and resilient, with many satellites having crashed or lost orbit due to the planet's halted rotation. Ground-based systems would once again become dominant. Fiber optic networks might connect settlements. Long-range radio might experience a renaissance. Technologies once seen as outdated would return, not out of nostalgia, but out of necessity. Yet for all the logistics, all the systems, the survival, something more subtle and difficult would take shape: the psychological reshaping of civilization. Human identity has always been tied to motion, the passing of time, the turning of days. Now that motion is gone, the world no longer moves around us, it simply is. That stillness, while survivable, might begin to eat at the human mind. Artists might depict the world not as it is, but as it used to be, chronicling sunsets that no longer happen, forests that no longer grow, waves that no longer crash. Musicians might turn to slow, droning sounds, echoes of a planet that hums but no longer spins. Philosophers would debate whether this stillness is peace or purgatory, and children, born into a world of twilight, would wonder why their ancestors ever thought motion was natural. Some may try to escape, not geographically, but psychologically. Virtual worlds, simulations of the spinning Earth, may offer temporary relief. In these digital refuges, the sun may still rise, the wind may still blow. People may log in not to play or work, but simply to remember what it felt like to be within time. Religion might surge or collapse. Some may see the end of Earth's spin as a punishment, others as a new beginning. Entire cosmologies may be rewritten, focused not on salvation or progress, but on stillness, balance, and survival. The dominant metaphors of motion, journey, growth, expansion may give way to new ones: rootedness, silence, endurance. Education would focus on new skills: how to maintain artificial ecosystems, how to preserve mental health in static environments, how to harness limited light, how to store and recycle every molecule of water. Knowledge would be passed down through tight-knit communities, not vast global systems. Literacy might survive, but with fewer books and more oral storytelling, legends and warnings etched into memory rather than text. And perhaps, far in the future, humans will forget the earth ever spun. It will become myth, like the gods of Olympus or the monsters of the deep. A story told by elders to children huddled in dome-lit shelters. Once the sun moved across the sky, and the children, listening with wide eyes, will ask, why would it do that? The twilight is more than a place. It is a condition of being, a liminal zone between past and future, between motion and stillness, between memory and myth. Here, human civilization will either endure or disappear, not because of fire or ice, but because of how well we adapt to silence. There will be no second sunrise, no rotation to bring change, only the light we make for ourselves. Chapter 8. The magnetic field fades. The Earth has always been more than stone and ocean and sky. Beneath the crust, deeper than tectonic plates or ancient fossil beds, something stirs that we rarely see or feel, yet depend on every second of our lives. It is invisible, silent, and powerful. It surrounds the planet like a cocoon, shielding it from the cosmic fury beyond. It is the geomagnetic field, and if the Earth were to stop spinning, this field would begin to fade. We often overlook the magnetic field because we do not interact with it directly. We cannot see its lines of force or hear its hum. But the field is there, extending tens of thousands of kilometers into space. It guides compasses, yes, but more importantly, it deflects the solar wind, the constant stream of charged particles emitted by the sun. Without it, our atmosphere would be slowly stripped away, our satellites would fry, and our skin would feel the sting of radiation not meant for surface life. The magnetic field originates deep within the planet's outer core, where molten iron and nickel swirl in turbulent patterns. This churning metal acts like a planetary dynamo. As it moves, it generates electric currents, and those currents in turn create magnetic fields. The result is a global shield, a geodynamo in constant, chaotic motion, stabilized in part by the planet's rotation. When the Earth stops spinning, that stability falters. At first, the magnetic field wouldn't vanish overnight. Its existence is rooted in the core's motion, which doesn't halt the moment surface rotation ceases. The molten metal would continue to flow for some time, retaining angular momentum inherited from billions of years of planetary formation. But the dynamics would change. The Earth's rotation exerts a stabilizing influence on the core's flow, shaping it into ordered, column-like vortices aligned with the axis of rotation. Remove that rotation, and the fluid motion becomes more turbulent, more chaotic, less capable of sustaining a coherent global magnetic field. This instability might lead not to a gradual weakening, but to something stranger, a magnetic reversal. Throughout Earth's history, the magnetic field has flipped many times. The North and South poles swap places, sometimes briefly, sometimes for hundreds of thousands of years. These reversals are not catastrophic in themselves. Life has survived them, but they are periods of weakness. The field diminishes, becomes disordered, and fragments into smaller, localized regions of magnetism. Satellites orbiting above would find navigation unreliable. Earth's surface would be exposed to higher levels of solar radiation. Auroras, those beautiful curtains of light, would appear closer to the equator and become more than just a spectacle. They would be a warning. In a world that has lost its spin, the likelihood of such a reversal or a complete collapse grows. Without the mechanical input of rotation to drive stable flows in the outer core, the geodynamo could weaken beyond recovery. The Earth would become magnetically quiet, and the consequences would be profound. The first and most direct impact would be on the atmosphere. The solar wind, once deflected by magnetic lines, would now interact directly with the upper atmosphere. Over time, it would strip away lighter particles, hydrogen and helium, bleeding the sky into space. This is not speculation. We see this process in real time on Mars, a planet with no significant magnetic field. Once, Mars had water, an atmosphere, maybe even life. Now, it is barren and dry, its air thin and unbreathable, its protection long gone. Earth would not become Mars overnight. Our gravity is stronger, our atmosphere thicker. But the process would begin, slowly, relentlessly. Radiation would increase at the surface. The ozone layer, already weakened by human industry, would face renewed assault from charged particles. More ultraviolet radiation would reach the ground. Skin cancers would rise. Crops would fail more often. Electronics would become unreliable, especially during solar flares, which could knock out power grids, damage satellites, or blind radio communications. And those satellites? Many would already be lost due to the cessation of Earth's spin as their orbits destabilize. But those that remain would face an increasingly hostile environment. Without the magnetic field to protect them, solar storms would erode sensitive components. Communications would falter. Navigation systems would degrade. The digital scaffolding of our civilization, already stressed by climate collapse and tectonic instability, would begin to crumble. In human settlements, especially those in the Twilight Zone, life would adapt to these new conditions. Protective architecture would be designed to shield inhabitants from radiation. Subterranean bunkers might become standard. Geomagnetic shelters, fitted with Faraday cages and electromagnetic insulation, would be required for sensitive instruments. New clothing materials would be developed, not just to insulate from heat or cold, but to block or deflect radiation. Still, the burden of constant shielding would change the way humans live. Outdoor time might become limited. Farming would move further underground or behind protective domes. Children might grow up never feeling sunlight on their skin. A new vocabulary would emerge, one not centered on weather or seasons, but on radiation indices, flare alerts, and magnetic silence. Navigation would suffer most of all. For centuries, humans have relied on the magnetic field to explore, trade, and connect. Birds, whales, and sea turtles do the same, using magnetoreception to guide their migrations. Without the field, these species would become disoriented. Migration routes would break, nesting cycles would fail, populations would crash. Even deep-sea creatures, those sensitive to the subtlest magnetic cues, would suffer. The ocean, already disrupted by temperature and salinity shifts, would lose yet another organizing force. Chaos would ripple down the food chain. And then there is the existential cost. The magnetic field is not something we see, but it surrounds us like a whispering veil. It connects us to the motion of the deep earth, to forces older than life itself. To lose it is not just a technical challenge, it is a symbolic rupture, a breaking of trust between us and the planet we were born from. The stars would seem brighter, the auroras more violent, and somewhere deep below the core would churn in silence, no longer shaping a shield, but slipping into entropy. A heart still beating, but without rhythm. Science would shift its focus. Entire fields of research would rise around magnetic restoration. Could we build artificial fields? Could massive orbital rings be constructed to deflect radiation? Could superconducting loops encircle cities, mimicking the planet's old defense? Some experiments would begin. Few would succeed. Others might embrace the loss. Philosophers and artists might come to see the magnetic field not as a right, but as a gift, something borrowed from a spinning Earth that no longer turns. They might paint in ultraviolet, sculpt in ferrofluid, or compose sonatas for a world without polarity. Children might learn history not by dates, but by field strength. Back when the field still existed, they'd say, like a fairy tale or a warning, and in time, if the core motion slows enough, the field may vanish entirely. The Earth would become magnetically inert. It would still be a planet. It would still have land and sea, light and dark, gravity and breath, but it would be stripped, exposed, bare before the sun and stars. Yet life is tenacious. Microbes in the deep crust would go on, oblivious. Fungi beneath the ice would continue growing. Life in geothermal vents, in darkness and pressure, would persist. Perhaps new species would evolve, not needing magnetoreception, not needing surface light. Perhaps they would see in radiation or communicate by electric field or live in harmony with the solar wind. Perhaps we would too, but we would do so changed. Because to lose the magnetic field is not just to lose protection, it is to lose memory. The memory of motion, of spinning iron, of a world that hummed with power even as it shielded us in silence. And when that hum fades, we will not hear it go, but we will feel the difference every day for the rest of Earth's still and silent life. Chapter 9. Life, but not as we know it. Life on Earth has always been shaped by the motion of the planet, from the simplest cyanobacteria to the complexity of human civilization. The 24-hour rotation of Earth has served as the invisible clock by which all life evolved. But if that rotation stopped, if one side of the planet was locked in perpetual sunlight and the other plunged into eternal night, then life, as we currently understand it, would cease to exist. That does not mean life itself would vanish, but it would change profoundly and in many cases irreversibly. In the earliest days following the cessation of Earth's rotation, most existing ecosystems would collapse. On the day side, constant solar radiation would increase surface temperatures to levels unbearable for nearly all terrestrial plants and animals. Crops would wither, trees would desiccate, insects, birds, and mammals would die from heat stress and water loss. On the night side, temperatures would plummet far below freezing, ice sheets would expand rapidly, entire forests would freeze solid, animals would struggle to find food or shelter and would die in large numbers. The twilight zone, the narrow band between the day and night sides, would become the new frontier for life. Here, the temperatures are less extreme, offering a sliver of survivability. But even in this marginal region, current species would find themselves facing unfamiliar and often insurmountable challenges. Photosynthesis, for example, is highly sensitive to light cycles. Plants evolved in a world of light and dark, relying on photoperiods to regulate growth, dormancy, and reproduction. In the twilight, light intensity would be low and unchanging. Only plants capable of functioning under constant dim light, possibly through specialized pigments or altered metabolic cycles, would survive. These might resemble shade-tolerant understory plants in today's tropical forests, or extremophile algae capable of existing near hydrothermal vents. Agricultural systems would need to be reinvented. Artificial lighting, hydroponics, and fully enclosed biospheres would dominate food production. But in nature, only the hardiest wild plant species would persist. Most of Earth's botanical biodiversity would vanish within decades. Animals would face even more pressure. Diurnal and nocturnal behavior patterns would lose their evolutionary function. The disappearance of daily cycles would disrupt circadian rhythms, leading to hormonal imbalance, disorientation, and behavioral failures. Migratory species, birds, whales, insects, rely on Earth's magnetic field and light cues to navigate. Without both, they would falter, unable to orient or time their movements correctly. In the sunlit hemisphere, only organisms capable of extreme heat tolerance might adapt. Some desert species already cope with high temperatures using methods like burrowing, estivation, and reflective body surfaces. But these strategies rely on the eventual return of night. Without it, heat would continue accumulating. Thermoregulatory limits would be reached. Even desert-adapted animals like camels or lizards would struggle, then perish. In contrast, the dark hemisphere would favor cold, hardy life forms. Organisms here would need to survive sub-zero temperatures, high pressure from accumulating ice, and extreme nutrient scarcity. Deep burrowing animals like certain rodents or amphibians might find short-term refuge, but food would remain a limiting factor. Only species capable of long-term hibernation, torpor, or cryogenic suspension would stand a chance. Microbial life, however, would fare much better. Extremophiles, microorganisms that thrive in hostile environments, exist today in conditions not far removed from what this future Earth might become. Thermophilic archaea flourish in hot springs and hydrothermal vents. Halophiles live in hypersaline lakes. Acidophiles survive in pH levels that dissolve metal. Psychrophiles persist in subglacial Antarctic lakes, metabolizing at near freezing temperatures with almost no sunlight. These microbes are likely to form the backbone of post-spin biospheres. In the Twilight Zone, communities of photosynthetic and chemosynthetic microbes might thrive in shallow water columns, soil crusts, or geothermal pools. On the cold side, bacteria capable of antifreeze protein production would colonize ice, snow, and permafrost. On the hot side, thermophilic colonies could exist in shielded environments like caves or under thick rock layers, where heat levels stabilize enough for life to function. Ocean life would undergo a massive transformation. Surface waters in the bright hemisphere would heat dramatically, leading to ocean stratification, layers of water that don't mix. This inhibits nutrient cycling, leading to marine deserts where phytoplankton can no longer survive. Coral reefs would bleach and die. Fish populations would collapse from starvation and overheating. But in deeper waters, conditions change more slowly. The ocean depths, already isolated from surface light and temperature shifts, may serve as a temporary refuge for some species. Hydrothermal vent communities, reliant on chemical energy from Earth's interior rather than sunlight, would continue largely unaffected, at least in the early stages. Tubeworms, clams, and thermophilic bacteria in these ecosystems may become key survivors, maintaining pockets of biodiversity even as surface ecosystems vanish. As centuries pass, the biosphere would begin to reconfigure. Evolution does not stop, it adapts. Given sufficient time, new forms of life might emerge from the surviving microbial pool, shaped by environmental pressures unfamiliar to any biology we currently know. On the hot side, organisms might develop heat-resistant proteins, cell membranes fortified against thermal denaturation, and light-harvesting systems designed to avoid photodamage. Such organisms may resemble today's cyanobacteria, but with biochemistry tailored for constant exposure to high radiation and low water availability. On the cold side, evolution would favor compact forms with antifreeze proteins, dormant spores, and slow metabolic rates. Instead of photosynthesis, these life forms might rely on lithotrophy, deriving energy from chemical interactions with rocks and minerals. In some cases, metabolism may occur only once every few weeks, months, or even years. The Twilight Zone, however, holds the highest potential for complex evolution. Here, life might gradually stabilize. With moderate temperatures and modest resource availability, ecosystems could re-emerge, different in structure but similar in function. Scavengers, decomposers, and predators may evolve from simple microbial ancestors, creating new food webs. Multicellular organisms may appear again, small, hardy, efficient. Perhaps insect-like creatures will dominate, cold-blooded, minimal in energy requirements, able to endure long periods without food. Perhaps new plants will evolve bioluminescent structures to attract pollinators in low-light conditions. Perhaps even new forms of vertebrates will arise, slower in metabolism, unfamiliar in form, but adapted to a world without a sky that moves. As generations pass, these organisms would no longer remember motion. Evolution has no memory, only function. The traits that no longer serve survival are discarded. Circadian rhythms would vanish. Vision might adapt to perpetual dusk. Biological clocks would reset. Life would not resemble what came before, but it would persist. Still, human observers, if any remain, might struggle to accept these changes. Our species evolved with expectations: sunlight that arcs through the sky, tides that rise and fall, stars that rotate across the heavens. We are wired for change, not permanence. Seeing life arise in stillness, quiet, altered, unrecognizable, might be unsettling. And yet in this still world, nature would continue its endless experiment. It would not rebuild what was lost. It would innovate within the new rules. Life is not a copyist. It is a problem solver. What would ecosystems look like in 10,000 years? Would vast fungal forests spread across the Twilight valleys, feeding off geothermal warmth? Would crustacean-like creatures drift through underground salt lakes, blind but precise? Would microbial mats cover the rocks, glowing faintly with engineered pigments to capture the faint ambient light? And if one day intelligent life were to re-emerge, what stories would they tell? They would not speak of a world that spins. They would not wonder why the sun does not rise. For them, the stillness would be normal. From the perspective of biology, Earth's rotation was simply one environmental parameter among many. Remove it, and life recalibrates. Not easily, not quickly, but eventually. There is no rule that says life must depend on spinning planets. There's only one rule: that life finds a way to use energy, organize matter, and pass along information. That rule still holds, even in a silent, frozen world. And so, though ecosystems collapse and species vanish and the biosphere contracts to a fraction of its former self, life goes on, not as we know it, but as it must. Chapter 10: The Slow Drift Toward Tidal Lock. Even if the Earth were to stop spinning suddenly, the story of its motion would not end there. For a planet, motion is not just a characteristic, it is a destiny shaped by the laws of celestial mechanics. And though the abrupt cessation of rotation would trigger catastrophe on every level of the biosphere, the long-term evolution of Earth's relationship with the Sun would continue to unfold. Slowly, inevitably. It is this gradual evolution that leads to one final, permanent transformation: tidal locking. Tidal locking is not theoretical. We see it throughout our solar system. The Moon, for example, is tidally locked to Earth. It rotates on its axis at the same rate it revolves around us, always showing the same face. Many moons of Jupiter and Saturn behave similarly. Mercury, too, once thought to be tidally locked to the Sun, is in a 3-to-2 spin-orbit resonance, still governed by tidal forces. In time, Earth could follow suit, not with respect to its moon, but with its star. If Earth's rotation were not just halted by a sudden catastrophic event, but instead slowed over billions of years, the Sun's gravitational pull would eventually synchronize Earth's rotation and revolution. One hemisphere would forever face the Sun, the other would never see it again. But even if Earth's spin stopped instantly, through some dramatic, improbable event, the forces behind tidal locking would still remain in play. Earth's gravitational interactions with the Moon and the Sun would begin to reshape its dynamics once more. And though the Earth would not spin, the Moon would continue to orbit. Over very long timescales, the Earth and Moon would eventually become mutually tidally locked, always facing each other in a strange celestial embrace. Later still, Earth's rotation, assuming some small remnant remained, would come into resonance with its orbit around the Sun. In this ultimate state, Earth would achieve solar tidal lock. One side of the planet would perpetually face the Sun, the other would exist in eternal night. This future is not one of violent transition. It is a future of long, slow adjustments. The process of tidal locking unfolds over millions, even billions of years. It occurs as gravitational forces between two bodies generate internal friction. This friction converts rotational energy into heat, slowly bleeding away angular momentum. The Earth's bulges, those subtle deformations caused by the Sun's gravity, exert torques that gradually slow the rotation. With time, the rotation period matches the orbital period. The lock is complete. On a stopped or already slow-spinning Earth, tidal locking would not be a cause of disaster, but it would signal permanence. It would seal the fate of hemispheres. The planetary divide between light and dark would not be temporary. It would be eternal. What would this locked Earth look like? It would resemble what we've already begun to see in the hypothetical aftermath of a stopped planet. The sunlit side would continue receiving solar radiation, constant, direct, and unchanging. Over the millennia, atmospheric and oceanic adjustments would reach equilibrium. The day side would be defined by a vast, permanent, high-pressure system. Without planetary rotation, Coriolis forces would not exist to break up circulation patterns. The weather would be stagnant. Winds would flow from the dark to the light side along the surface and return aloft in slow, predictable convection cells. The result would be a superheated zone near the subsolar point, the place where the sun stands directly overhead, unmoving. Around it, temperatures would taper toward the terminator, the twilight zone that separates day from night. The land beneath the subsolar point might turn to desert glass. Silicate sands fused by constant sunlight. Even rocks could break down over time, degraded by extreme thermal cycling and solar radiation. Solar panels, if maintained, could generate unlimited power, though the machines tending them would need to survive extreme heat. In the sky, the sun would hang in the same position for all time. No sunrise, no sunset, just a permanent noon. Shadows would never shift. The passing of time would no longer be measured in days, but in years, in orbital cycles around the sun that mark a year, but not a day. On the dark side, the cold would deepen further. No residual heat from previous cycles would remain. Ice caps would thicken until they reach a new equilibrium, balancing geothermal heat from below and radiation to space from above. Temperatures would stabilize at levels far below anything seen on modern Earth, rivaling the coldest parts of Pluto. The sky would be dense with stars. The Milky Way would glow as a fixed structure, unmoving and sharp. Time would pass here in silence, beneath a sky that never changes. Over the centuries, the atmosphere would adjust to the new configuration. Heat transfer from the bright side to the dark side would form a slow planetary circulation, perhaps 2 or 3 global Hadley-like cells transporting air along vast loops. Winds would not be fierce, but they would be ceaseless. From the surface of the dark side, high-altitude clouds might be visible, moving faintly from horizon to zenith, bearing moisture from the other side of the world. Oceans, by this point, would have migrated toward the poles and dark side, reshaped by both gravitational rebalancing and atmospheric drag. The hydrological cycle would be minimal. Precipitation would fall primarily near the terminator, perhaps forming a ring of constant rain or snow along that frozen borderland. Rivers would flow inland, but few would return to the sea in a world without spinning currents or dynamic tides. Life, if it had managed to adapt through all prior stages, the stopping of Earth's rotation, the collapse of weather, the fading of the magnetic field, would now face its final test. Not one of survival amid chaos, but of permanence. A locked Earth is a still Earth. Stability replaces variability. The ecosystems that do endure would need to evolve for constancy, not change. Perhaps some life survives underground, near hydrothermal vents or geothermal outflows where temperatures remain habitable. Perhaps microbial colonies thrive in the terminator zone, feeding off gradients in temperature and moisture. Perhaps a small human population carves out existence in high-tech enclosures, using stored energy, recycled air, and artificial ecosystems. But for most of the planet, the age of biology would fade into geological time. Above this frozen landscape, the moon, now likely tidally locked in perfect orbit with Earth, would hang in the same portion of the sky, unmoving, a companion not circling, but gazing. The Earth-Moon system, once dynamic and gravitationally active, would become a fixed duet, locked in place, a frozen dance. And still, the Earth would move around the sun. A year would remain a year. But without rotation, the fundamental structure of life, days and nights, growth cycles, migratory routes, and circadian rhythms would be long gone. All that remains is the orbit, the elliptical path of a once spinning world around its stellar anchor. For astronomers far from Earth, looking back across the void, our planet would appear as a world of contrast. One half glowing brightly, reflecting constant sunlight, the other dim and infrared cold. Unlike other planets that show regular light curves from rotation, Earth would display little change over short intervals. It would be a planetary coin, one face illuminated, one face hidden. Tidal locking, in a sense, is the universe's way of conserving energy. When friction, gravity, and motion reach equilibrium, what's left is stillness. Celestial bodies turn toward one another and settle into stasis. For Earth, the loss of spin is not just an end, but a conclusion. It is the final chapter in a long narrative of motion. From the swirling of dust in the early solar system to the planetary accretion that gave us a rotating world. From billions of years of rotational slowing aided by the moon to the sudden or gradual cessation of spin, from cataclysm to equilibrium. And in that stillness, Earth becomes something else. No longer a world of change, but a monument to what came before. The planet will remain. It will orbit, its crust will cool, its atmosphere may thin, its oceans may freeze, but it will endure a locked world, a final world. Earth as the sun always sees it, half a light, half shadow, and forever still. Thank you for spending this time with me, exploring the quiet unraveling of a world that stops spinning. I hope it brought you a moment of stillness, a space to wonder, and perhaps a gentle path toward rest. If your eyes are already growing heavy, let yourself drift, safely, peacefully, into sleep. But if you're still awake and your mind is still wandering through the stars and silence, there's another journey waiting for you. Just below, you'll find a story designed to carry you even further into calm. Until then, sweet dreams, traveler, and may your world keep gently turning, even if only in your dreams.